Hey, my name is Aaron. I am one of the lab TAs this semester. I'm going to run you through the first part of our lab. We're going to take a brief overview of what we'll be doing. First, we'll begin by examining the lab equipment. Since it's going to be different from TA to TA, be sure to take note of it in your notebook. Then we'll run through a few basic circuits, take some measurements. Be sure to note these measurements in your notebook as we will be turning them into a table and eventually plotting them in Excel. Okay, first we're going to have a brief overview of the equipment involved in the lab. Uh, First up, we have our power supply. This is going to vary from TA to TA. As you can see, we are working with a Tech Power TP3005T. You can see it displays voltage on top and then an approximation of the current draw on the bottom. Note next to the CV, there is a green light lit up indicating it is in constant voltage mode. You can change it from constant voltage to constant current depending on your application. We will not need to adjust that for this particular lab. Next up, we have the Ragu 81D. This is a multimeter with auto ranging. As you will note on the bottom, from left to right, there is a 10 amp marking, which indicates for high current measurement. We have our COM or common. This is our ground reference from what we're measuring. And then on the right, we have volt, ohm, milliamp, diode, continuity, hertz, and there is a capacitive check, but I have not used it personally. Additionally, you will note on the right there is a 400 milliamp max fused for that plug. So if we tried to measure beyond 400 milliamps, that fuse would blow and essentially render that measurement capability useless on this meter. This is why we have the 10 amp plug if we know that we're going to measure anything larger. For this lab, we will not need to adjust that. And of course, we have the humble breadboard. This is going to be what we connect to in order to make our measurements. You will see that there are columns along the outer edges. This is generally used for your power sources and ground. They are denoted, there we go, by a red and blue stripe down the edges, as you can see here, but ultimately it's all dependent on what you connect into it. The wires go across in rows. There is a gap here which breaks the wires going across. So wires, unless they're connected, do not jump the gap. And over here, we'll turn down the light so you can see we have a simple breadboard that's running a 12 volts regulator. As you can see, we have wires going into ground. We have extra wires that are more apparent up top that jump from the top half to the lower half. Not all of the breadboards will have continuity through the entire strip. And then coming back out, we have our power and our ground running back to the power supply. It is good practice to use wires to connect onto your power supply. We could just as easily plug in this connector to the appropriate positive lead, but it can lead to some issues if something gets bumps, shorts, and causes stuff to blow up. Ideally not your power supply. To measure with the multimeter, as you can see, we've got our red wire going into our volts ohm plug. We have our black wire going into the common plug. Now, it is good practice to short out the tips so you can get as close to zero on your multimeter as possible. So first, we're going to do just a couple sample measurements. This is not anything required, just to demonstrate how we're going to work. So first, we're going to take the black probe and we're going to make sure that we touch metal on our board. This is touching the negative rail, as you can see here. And then we're going to touch the positive rail and see if we can get our output voltage measured. So we'll go right here, and 14.98, which is approximately 15 volts. Now this is a 12 volt regulator, so we should see an output close to 12 volts. And if we measure, we are getting 12.05. Fantastic. Now, if we need to measure current, that is a slightly different proposition. So first, we're going to look at the power meter. Looks like we're using approximately 11 milliamps, so we should be safe to use the 400 milliamp max plug. So first, we're going to change it to the milliamp range. And in order to connect it, you have to create a break in the circuit, or basically you have to separate the circuit so the current goes through the multimeter. We're going to do this by first rotating this resistor so the two lines are no longer connected. Then we're going to add in a point for the multimeter to connect on one side and then on the other, which completes the circuit. So the multimeter ultimately will be acting as a wire that just happens to sense current. So we'll jump back up here so we can see the measurement. We'll reconnect the power supply. As you can see, it's only 6 milliamps, but that will change as we connect our meter. So we're going to take one of the leads. This is the negative side. We're going to touch it to the multimeter lead. We're going to take our yellow wire and do the same. As we touch, lights back up, and this time we're measuring 4.54 milliamps on the Ragu 81D. You will note that this is different from the power supply output. This is because this is being measured through the 12 volt output. A small note on resistors. Yes, you can measure them to determine the resistance, but you generally can find out with through-hole resistors what they are based on their color code. Now, some resistors, especially the ones that you buy off of Amazon, are going to have several more bands, as you can see on the left, than the resistors you will get from the school shop. The resistor on the right has 4 bands. That goes green, brown, orange, and then it's difficult to make out on the camera, but the last band is gold. This determines the resistance. So in this case, green is 5, brown is 0, and orange in this case is for 10 kilo ohm with a sensitivity of plus minus 5%. The resistor on the left has a color code brown, black, black, brown, brown, which this means it's in this case a 1, 0, 0, 1 with a sensitivity of plus minus some percent. I'm not certain on this particular brand, but it comes out to being a 1 kilo ohm resistor. This resistor is what we're going to be using in the lab from here on forward. Now we're going to start off by demonstrating a very simple circuit. We are going to take a 1 kilo ohm resistor, as you can see here, and we're going to measure both the voltage and current through it. Seeing as we only have the 1 meter, we're going to be doing one measurement of the voltage. That's going to be done across positive terminal and the negative, which is tied to this green wire for easy access. And if we measure it now, the current voltage on the power supply is set at 0, and we are getting approximately 0 of 0.0016 volts, or 1.6, 1.7 millivolts. So first, we're going to step up the voltage to 0.5. And we'll measure. So our digital multimeter confirms we are at 0.5 volts. So next, to measure current, we're going to switch this over to milliamps, and we're going to close the circuit. And as you can see, we are measuring 0.48 milliamps through this circuit. This is not even registering on the power supply and demonstrates the value of having a separate ammeter in your circuit. Next, we're going to step up to 1 volt. So break the circuit, switch back to the voltmeter, and we'll step it up. As before, we're going to measure and confirm that we are getting approximately 1 volt. Fantastic. Switch to milliamp. Once again, we're going to complete the circuit with our ammeter, and we are measuring 0.98 milliamps. We'll continue the progress up to 1.5 volts. Back to volts. And we are getting a voltage of 1.5 volts. Fantastic. We'll complete the circuit after we switch to current mode. And we get a current of 1.47 milliamps. And we're going to keep up this process until we reach 5 volts. Next measurement at 2 volts. And there we go. Sometimes you need a good connection in order to get a stable reading, which is 1.999, briefly flicking over to 2 volts. Close enough to 2 for us. We'll switch to milliamps. And once again, we're closing the circuit. And we are getting 1.96 milliamps through our circuit. Up to 2.5 volts. Once again, let's switch to volts. And we are measuring 2.499 volts, or approximately 2.5 volts. Now we'll switch up, measure the current through the circuit. And we are getting 2.45 milliamps. Up to 3 volts. And we switch back to voltage. We are at 3 volts indeed. Switch over to current. And take a brief measurement there. And we are getting 2.95 milliamps through this circuit. If I can get, there we go. All right. Now we're going to move on up to 3.5 volts. Once again, we'll measure 3.498 volts, approximately 3.5. We'll switch to milliamps. And we are getting 3.44 milliamps out of the circuit. Up to 4 volts now. We'll measure, and we are getting 3.998 volts, approximately 4 volts. We'll switch to our milliamp range, and we are measuring 3.92 milliamps approximately through the circuit. Switch up the voltage. We are now at 4.5 volts. We'll measure with the multimeter to confirm. .49 volts, approximately 4.5. Excellent. Switch up to our milliamp scale. And we are measuring 4.49 milliamps through the circuit. And then our final step. Measure the voltage across our rails. We are at 4.99 volts. Switch up to our milliamp range. And we are getting 4.92 milliamps through the circuit. So this method of measuring has shown that our power supply is reasonably accurate, at least as far as our multimeter can determine, and we are able to measure the currents fairly easily based on that. We can use the assumed value of 1 kilo ohm to determine the appropriate value, but this is not going to be always exact. So we're going to take a quick measurement in ohms of our resistor. OL means open loop. So if you're getting open loop, you're either measuring something well beyond the capability of your multimeter, or you are measuring air. So if we short the leads together, we are going to get a very small value, 0.2 ohms. So next, we're going to measure our 1 kilo ohm resistor just to be certain that we are getting something valid. And our auto ranging is going to find the resistor at 1.002 kilo ohms. Next, we're going to slightly rearrange the setup so we can do more measurements at a quicker pace for different resistors. Now that we've demonstrated through repeated measurements that our power supply is putting out approximately the voltage that we want, we can go ahead and use the appropriate voltage displayed on the supply as our reference. Anything off by 1 or 2 millivolts on the scale of volts is not going to make a large difference. We have our ammeter set up so we can measure simultaneously voltage and current through the system. First up, we are going to switch our resistor out, and we're going to use a 50K resistor. This is our green, brown, orange resistor. Just to be sure, we are going to take a measurement. And our meter agrees. We are measuring about 50.5, 50.8 kilo ohms within margin of error. So we're going to reconnect this to our circuit. And we're going to reconnect our circuit back the way it was. So now we have our power coming in on this rail. Let's see, there we go. We have that running into our 50 kilo ohm resistor, which goes up, comes out of this yellow wire, runs into the ammeter, comes back out, and goes to ground, which goes back to the power supply. So we'll start our measurements here. At 0 volts, obviously, we're going to have 0 current through our system. Let's increase the voltage to 0.5 volts. And because we're using a very high value resistor, approximately 50 kilo ohms, we are not going to be able to pick up anything on the milliamp range. So we're going to step it up to microamps, or 10 to the negative 6 amps. At 50 kilo ohms, we are measuring 9.8 microamps through the circuit. We're going to start increasing the voltage up to 1 volt, and that increases the current through the circuit to 19.6 microamps. 1.5 volts, and that jumps up to 29.5 microamps through the circuit. Up to 2 volts, we are getting 39.3 microamps through the circuit. Up to 2.5 volts, we are up to 49.2 microamps. And up to 3 volts, we're at 59 microamps even. Up to 3.5, we're looking at 68.8 microamps. And up to 4, we're jumping to 78.7 microamps. 4.5 volts, we are up to 88.5 microamps. And our last measurement for this resistor at 5 volts gives us a current of 9.83 microamps. Let's go ahead and turn down our voltage back to 0. Alternatively, you could turn it off, disconnect it from the circuit. Any of these would work. So we'll take out our resistor. Our next resistor that we are going to measure is 100 ohms. The color code on that is brown, black, brown, gold, indicating it is 100 ohms. And we're going to double check on our meter. And we are getting a resistance of 99.5 ohms. Now, according to Kirchhoff's Ohm's law, we are going to have approximately at 5 volts, 5 volts divided by 100 ohms, that's going to be about 50 milliamps through our circuit. So that should be acceptable for our 400 milliamp fused reading, so we don't have anything blowing up on us. We're going to reconnect the circuit, switch it back to the milliamp range for this. And we're going to start increasing the voltage. Once again, at 0, we are expecting 0 milliamps, and that is what we have. At 0.5 volts, we're measuring 4.56 milliamps. up to 1 volt, we have now jumped to 9.11 milliamps. You'll notice a discontinuity between what's being measured on the meter versus what's being displayed on the power supply. Again, this further supports the need for a secondary measurement device. We'll go ahead and increase the voltage up to 1.5 volts. And we are measuring a current of 13.69 milliamps. Continue to step it up. At 2 volts, we are getting a current of 18.37 milliamps. At 2.5 volts, we are up to 22.98 milliamps through the circuit. And at 3 volts, we are looking at 27.61 milliamps through the circuit. .5 volts yields 32.24 milliamps through this circuit. And at 4 volts, we are seeing 36.89 milliamps through the circuit. At 4.5 volts, we are seeing a measurement of 41.56 milliamps, which is rather close to what is being displayed on the power supply itself. As you work away from fringe measurements, either near the bottom or the top end of the supply's capability, it will get more accurate. Some deviation is impossible to avoid at the top ends. Again, further reinforces the need for a secondary measurement device. At our final voltage of 5 volts, we are getting a current of 46.3 milliamps. Again, you can see the slight discrepancy between the power supply and the multimeter. We are looking at what is a kilo-ohm resistor. It is difficult to see under the camera with a background, but that is a red band on the left. The color code is red, black, black, brown on this resistor, indicating it is a 2 kilo-ohm resistor. We are going to measure just to be certain. Switch to ohms. And connect our leads. .992 kilo-ohms. Close enough to 2 for us. Go ahead and reinsert it back into the circuit. Switch the meter back to current. All right, so we're going to start our measurements out at 0.5 volts. And we are getting a current of 0.24 milliamps. Jump up to 1 and 0.49 milliamps. .5 volts, 0.74 milliamps. Up to 2 volts, we are looking at 0.99 milliamps, almost a full milliamp. At 2.5 volts, we are at 1.24 milliamps. At 3 volts, we're looking at 1.49 milliamps. At 3.5 volts, we are looking at 1.73 milliamps. At 4 volts, we are looking at 1.98 milliamps. At 4.5 volts, we're looking at 2.23 milliamps. And at 5 volts, we are looking at 2.48 milliamps. So all of these values that we have measured through on all resistors, we're going to go ahead and take a moment and tabulate them into a table. You will see what we're expecting to see in your notebooks roughly. All right, we've got our table in Excel populated. We've got our top row filled out with the different voltages that we tested at. We have our resistances, their measured values. Now Excel doesn't like to play nice with large numbers, so we're going to go ahead and just change them over to a general number. So if we turn that back, excellent. We can see 99.5, the 1001, 1992, 50,800. That's basically going to come up later after we touch on this table business. As you can see, we have the associated measurements and the resistance on the left. You do not need to use the ohm symbol when you're creating your plots. However, it would look professional. Now, to create your plots, I recommend that you have them in a similar shape. Excel is not as difficult as it used to be. So we highlight everything, and if we insert under our recommended charts, we should see a proper line chart. Now this is a great start. We're able to see approximately the same shapes for each of these measurement sets, but to make it look proper, we'll go up to the quick layout and change it so we can include some relevant measurements. So we're going to set this to current. We are working in milliamps. We're going to set this to voltage. We're just working in volts. Of course, we'll want to give it a title. And bam. Now we can improve the resolution of it kind of for most of these. However, the 50 kilo ohm is really small, so it may as well be a flat line on this scale when compared to 100 ohms. Be sure to take a moment, and you can do this in Excel, you can do this in MATLAB, you can do this in Maple, any number of tools that are capable of creating plots you're welcome to use. Be sure that it's using the recorded data from your lab. So when you're working on your graph, be sure to include some commentary in your notebook. Questions like, what is the shape of the graph? If it's linear, find its slope. You can use either straight mathematics to use that, or you can use Excel. I know there is some slope functionality built in. Be sure to comment on whether or not this graph demonstrates Ohm's law. Anything else that might come to mind as you observe this experiment. We will now explore measured resistance value versus the expected resistance value. First, we're going to create a chart which contains a nominal resistance, the measured resistance, which we have in the second row, and the calculated resistance. The calculated resistance is going to be comprised of Ohm's law, which is V equals IR, or in this case, to find the resistance, we're going to do V divided by I equals R. In this case, we've got our associated values with our measurement at 5 volts. This is our current. We had to change it to be an actual number instead of in milliamps like we saw previously. And we've taken these values and plotted them on the chart here. The axis titles are not populated currently, and we can change those just by clicking into them and renaming things. But at this point, this is approximately what you will see when you create your own plots. In your notebooks, be sure to note the shape of the graph, its slope, what it means. Be sure to note the differences between the reported, measured, and calculated resistances. How do they differ and why? And anything else that might be interested about this way of looking at the data.
Hey there, my name is Sam. I am another one of your lab TAs here. This is my third semester TAing for this class, so I've been here for a while. Yeah, and so I just wanted to, first things first here, give a quick rundown of my gear that I'm going to be using for this lab because it's a little different than what Aaron uses. He's got gear that's very similar to what we use in lab, and I have more at-home use stuff. So, the main core that I have is this guy here. This is called an NI MIDAC, National Instruments MIDAC. DAC there stands for data acquisition. And this guy in and of itself is basically a whole at-home lab kit. So it does just about everything you could want. It's got a multimeter, an oscilloscope, a function generator, all sorts of stuff. The main things we'll be using for now are the multimeter and the function generator. So I would strongly suggest something like one of these if you are a hobbyist, you want to do some of these labs at home, anything like that. The stockroom in Merrill Engineering Building has something similar. They're called the Analog Discovery 2s, or AD2s, and they're very similar, just slightly different design, but they do all the same things. Okay. So what's really nice about this guy is it's just USB, and let me plug it in here. And then once it's in, we can. So this is the display of the multimeter here. Um, and I can show you how it works really quick. So just like any other multimeter, you can see we can measure DC and AC voltage, DC and AC current. It also is able to do resistance and impedance, or sorry, capacitance and inductance, as well as testing diodes. So it does a lot of things here. So we are just going to attach these two little probes to our MIDAC. And let me grab a resistor out of my kit. I'll just grab a random one. This is a brown, black, yellow. I think that's 1K, but I'm not great at remembering what they are. So let's pop over to the multimeter to figure it out. I'm going to set it to measure impedance, and I'm going to set it to auto mode, so it'll just pick a range for me. And I can tell it to begin running. And now when I make contact here, we are going to get a good reading. There we go. It's reading about 86 kilo ohms. That's partially because I'm messing it up by holding it. Should be closer to 10K. So let's throw it in the breadboard. So here I just plugged it into the breadboard, so I'm not making contact with it anymore. And when I measure that, now we've got 98K ohms. right? So sorry, that should be really close to 100 k ohms, which is what this guy's resistance is. So yeah, the nice thing about these Midax and the 82 is that they are relatively cheap. This guy was like $230, I think. I've used it for all 4 years of my college career. The Midax are 300. But if you get them from the stockroom, you can actually return them at the end of the semester for most of your money back, which is nice. All right, awesome. So let's get rid of this for now and take a look at our lab. So we are going to be continuing on from where Aaron left off. So we are going to be looking at Kirchhoff's law and simple equivalent resistances. Sorry. So first things first, for Kirchhoff's law, we are going to be building this circuit here and placing our voltmeter in 2 different locations. So please draw that circuit in your notebook and describe what we're doing here. So what circuits are we using? What resistors are we using? And what is our goal, right? So here we're placing 2 resistors in series with a voltage source across them. Then we are going to measure the voltage across each resistor individually and also measure the current through each resistor. And we will be attempting to answer these questions here. After we do that experiment with them in series, we're going to do the very similar thing with them with the resistors in parallel here. This time kind of more focusing on the current, so we'll be using an ammeter. All right, so let's start building a circuit. Okay, so here we have our circuit board, and we just want to get started building that circuit that was defined in our PDF. So first things first, we need to find a 1 k ohm resistor, right? And so the color code for that is going to be brown, black, red. I've got a whole bunch of resistors in here, but this looks like brown, black, red here. If the camera will focus on it, there we go. Red, black, red. And just to double check, I'm going to take my multimeter and let me throw this guy in the breadboard, and then we'll get a measurement. Go this direction. So, of course, note here that the legs of the resistor are in 2 different rows, right? Because our rows are connected going across. So having them in 2 separate rows guarantees that we're not shorting this resistor out. Okay. So now I will take my probes, which are connected into my multimeter, and touch on here. Oh, I may have to start the multimeter again. Gotta press the run button. Perfect. So that is 0.99 k ohms, which is exactly what we're looking for. We're looking for 1 k ohm. All right, great. So next up, we are going to need a 2 k ohm resistor. So for this, we need a red, black, red, which I have right here. So here you go. You can see that. There you go, red, black, red. So I want this to be wired in series with this resistor that I have down here. And it's looking like the glare is making this a little bit difficult to see. Let me see if I can do anything to fix that. Okay, I'm hoping this makes things just a little bit easier for you to see. I just changed some camera settings here. All right. So next up, we've got our 2 k ohm resistor right here, red, black, red. And we're going to throw that in series. So that means they are going to share 1 row, just like that, right? You can probably kind of see right here how these 2 legs are in the same row. And again, we can verify that this is a 2 k ohm resistor by just throwing these guys on either side. And as you can see right there, we've got almost exactly 2 k ohms. Great. So next we need to wire in our power supply. So let me throw on, that's a function generator. That's not actually what I want. I want a digital power supply. Gonna find our function generator can work. It can produce a DC signal. Um, but I think we want a DC level output rather. So let me change this. All right. So this window now is showing us our level output. Um, it's giving us a little bit of information. So it's saying A00 is our channel setting. So that refers to this pin here. So A00 is going to be A0, and 0 is this number here. So that's saying, telling us where the signal will be coming out of there. And then we also need to connect our ground. So it's standard to use a red wire to signify high voltage and a black wire to mean low. Um, that doesn't actually mean anything. It's just standard to know that and to do that. So I'm going to plug my red wire into port A00. You actually need a screwdriver on this to tighten it down. And then my black wire, I'm going to go into ground. So the way that these ports work is they've just got a little screw over them. And we've got these little prongs on these wires that stick into the port. And then you want to tighten down the screw so that it doesn't move. So it's actually pretty tough. I'm not going to pull too hard because I stripped this wire, but it's actually pretty hard to remove this right now. So now I'm going to throw my red wire in my circuit. This here. I'm going to take this red wire and plug it in to my breadboard right here. And the black wire is going to go right there. All right. So that is our basic circuit. This is the same circuit that is described in that first part of the Kirchhoff's law part of our PDF. Right. So now we want to apply a voltage across here. And it doesn't look like our PDF specifies a voltage, so we can pick whatever we want. I'm going to go for, let's go for 5 volts. Actually, let's go just for 2 volts. I don't want to accidentally burn anything here. Just 2 volts. All right, and I'll start it. And there we go. Now we are outputting 2 volts from this MIDAC into our circuit. Right? Nothing really interesting is happening yet. So this is where our multimeter comes in. So we're once again going to take our 2 probes. And now, rather than measuring resistance, we are going to measure voltage. So I'm going to set this to measure DC voltage. It's still going to take the auto range because I don't want to do the work of setting that range myself. And now we will begin running that. So that starts our voltmeter. It's not going to read any voltage until we touch to these 2 guys. All right. So it looks like across our 1 k ohm resistor, we are reading 0.667 volts. Right? And across our 2 k ohm resistor, give it a second, we're reading 1.3 volts. Or 1.334 volts. Right? All right. And of course, just to verify, if we measure across both, we should be reading just about 2 volts. Because that's what we're putting out there. All right. So now using that, try to answer these first few questions in the lab notebook. So here is asking, do Kirchhoff's laws stand for this example? How can we know? And why are the voltages across the two resistors different? We will come back in just a second to these last two parts here. So see if you can get these guys. You can pause the video here while you're answering. And now I will go on to read current values. Okay, so now I'm going to go measure the amperage of this. So measuring amperage is a little bit than voltage because we actually have to break our circuit and throw our ammeter in the middle to reform that connection. So we're going to break our circuit by pulling the top leg of this resistor out so that it's no longer connected to our voltage source. And we still want it to be connected to our other resistor. So I'm going to put it in sideways like this. So this bottom leg is still connected to this resistor, but now our power is disjoint from this leg here. So now we need to tell our multimeter to measure amperage, which it's already on, it's on DC amps. And we actually need to move this pin here. On my multimeter here, you can see here it's got a V and an ohms for what you can measure in these, and then an A over here for that we'll be measuring current with this port. So we have to move this red one down to here. It's pretty common to have to move things around to measure current rather than voltage. All right, and now I'm just going to put these probes in the rows here. Got to push pretty hard to make contact. Let's see, should be measuring something. Oh, sorry, somehow my ground got disconnected. Can't have a complete circuit without a ground, so that would be why we were not measuring any current. So let's try that one more time. And there we go. We're getting 0.68 milliamps. Now this is important to note that this is going into that first resistor there. So if we are looking at our lab notebook, this would be the current going into this resistor here. Okay. So next we are going to change it up so that we can measure the current in going into our second resistor. So we're going to rewire. We're going to replace this first, the 1K resistor. Okay. And now we're going to break it such that so that we are no longer making contact with that, so that this 2K ohm resistor is no longer connected to the 1K ohm resistor, right? And now we will replace our high voltage and our ground like that. And now we just need to take our ammeter and form that connection between our 1K ohm resistor and our 2K ohm resistor. And we are once again measuring 0.68 milliamps. Okay. So maybe a little bit difficult for you guys to see what I'm doing here, just because my hands may be blocking stuff, but to try to get a grasp on what exactly went down there. All right, and now you can answer these last two questions about this first circuit. How are the current values related? So we measured both the current going into the 1K ohm resistor and the current going into the 2K ohm resistor. And then the question is, anything else interesting that you might notice about this experiment? So fill those in, and then we'll move on to the next part. So next up, we are going to build a parallel circuit. So we're changing things up a bit. While we're building this, I'm going to turn off my output, my PC output, because I just don't want to be having loose voltage here, because I could shock myself or cause other damage. All right. So in order to make our parallel circuit, we're going to take this 2K ohm resistor, we're going to plug it down into our breadboard. Just like that. I'm sorry, let me change my camera. Okay. And then we're going to take our 1 k ohm resistor and put it in the same rows as our 2 k ohm resistor. So they should share both rows like that. Okay. And now we're going to put ground here on the bottom in the same row as them. And our high voltage is going to go right here. Okay. Now, if we refer back to our PDF, we can see that we are going to want to measure this current going into our entire junction. And then measure the current here, and then measure the current here. So I strongly suggest you draw all 3 of these circuits just to be very clear about what currents we are measuring, so that you can understand what we measured here. And you should label each of these. So this could be I1, I2, and I3. This one could be I3, and so that way we can keep track of what we're measuring. Okay, so for this one, we're going to do current first, and then we'll grab the voltage measurements afterwards. Okay. All right, great. So in order to get that first current that's going into everything, I'm going to need to separate our high voltage. And, oh, let me turn on our voltage generator again. Go. And we'll take our red and form that connection between our high voltage and both of our resistors. Okay, so that I1 is looking like 2.29 milliamps. Okay, 2.29 milliamps there. Alrighty. All right, so next we're going to want to measure just the voltage going into our 2 k ohm resistor. So I'm going to stop this voltage source for just a minute while I rewire this. I'm going to make it just like this. So what I've done here is I've separated things out so that our voltage source is connected directly to our 1 k ohm resistor, but it's disconnected from our 2 k ohm resistor. So now, when I take my ammeter and form this connection between these 2 rows, I'm now putting the ammeter exactly where it is in our PDF photo. So I'm putting it in like this, so that we can only read the current going into our 2 k ohm resistor. Okay. So obviously we're reading nothing because my voltage is off, so I'll turn it back on. And let's see what we're getting. So now just this 2 k ohm resistor is getting 0.76 milliamps. Okay, so make sure you record that. I2 is 0.76 milliamps. All right. And now the last thing we want to do is get just the current going into our 1 k ohm resistor. So we're going to just switch these guys up. So now, as you can see here, our high voltage is connected directly to the 2 k ohm resistor. And then I'm going to use my ammeter to form the connection between that row and the 1 k ohm resistor. Okay. So let me start up our voltage source again. And now we're reading 1.53 milliamps going into our 1 k ohm resistor. Yeah, 1.53 milliamps there. So make sure you record that. And that is what we've got there. All right, great. So using those measurements, you should be able to answer now the first 2 questions here. Right? Why are the currents across the 2 resistors different? And do Kirchhoff's laws stand up for this example, and how can we know? All right. And now we're going to go back here and take voltage measurements. So voltage measurements are much easier. We'll just make our circuit once more. Just okay. And note that I usually remember to turn off our voltage whenever I'm changing up the circuit. It's good practice to change it, to turn off your voltage source, because you could potentially shock yourself or fry some electronics. I'm just dealing with 2 volts, so I'm really not going to do any damage. And I probably wouldn't even feel a shock right now. So that's really not much to worry about. But it's good practice to do anyway. All right, so let's start up our 2 volts again. And let's tell my multimeter to measure volts. And we're going to have to switch this back over to this port here on the multimeter. And it looks like our measurement is going. So I'm going to first measure across the 2K ohm resistor. That's this guy. And it looks like we are reading 1.5 volts DC. 1.5 volts. Which is interesting. And now if we measure the voltage across our 1K ohm resistor, we're also measuring 1.5 volts. All right. So the reason for that, why is that not 2 volts, right? We would expect it to be 2 volts. I believe that the voltage source is being limited by the current draw here. I think this is trying to draw too much current, and so it's having to bring down to 1.5 volts. So you'll actually see if I take this level down to just 1 volts. If I do that, now when I measure what's here, see we get 1 volt and also 1 volt here. All right, perfect. So yeah, those measurements are now equal to what our voltage source is putting out. And so that was just an example also of the limitations of some of these at-home kits, right? They really can't put out that much current. And so you'll sometimes have to be limited by just what your gear can do. And so I wasn't able to measure the response with 2 volts there. I had to take it down to 1 volt. In this case, we're measuring just about the same thing. All right, so now you want to answer these questions. How are the voltage values related? And is there anything interesting about this experiment? So once you get answers for that, you can come back to the video and we will start up with the next section. So next up, we are going to do a simple equivalent circuit. All right. So we are going to take 2 1K ohm resistors. So we need our brown, black, red resistors. So I've got my 1 from the last circuit, and I need to find 1 more. Brown, black, red, this guy right here. There we go. So we've got 2 of them. And I'm going to set them in series with each other, just like what is in our PDF here. So just like this circuit here, I'm going to have both of my 1K resistors in series. Okay. Okay, so yeah, first thing we want to do is we want to take a measurement of the current going through these 2 resistors going into this circuit. As we see here, we want to take this current going this direction. And then we want to use Ohm's law from a 5-volt source to calculate the resistance of these guys together. So of course, Ohm's law being V equals I times R. V will be our Vs. I will be whatever we measure here. And then we're going to calculate R based off of that. Okay. So now last thing we have to add here is our ground, of course. Just to make this easier, I'm just going to move this resistor to the other side so I can put my ground there. And I'm going to disconnect, of course, the voltage source from our start of our circuit again here because we want to use our ammeter to form that connection. So we can measure the current going into our circuit. So let me turn this into an ammeter. I will set my voltage source to 5 volts. Hopefully we can output that. Let's see. And we will form this connection. All right, it looks like we're getting 2.25 milliamps on that as our I value. right? So you use that and 5 volts to calculate what our resistance is here. Right? Once you've done that, we can move on to our next calculation. Okay, so next up, we're going to want to take 5 different measurements, including that one we just took, with different resistor values in here. So just as a reminder, this current here with 5 volts and our two 1 kilo ohm resistors is 2.24 milliamps, right? So let's switch this guy out. Let's take this one out and replace it with a 2K ohm resistor. And let's see what we get as our current going in here. So please be making a table of this data showing the voltage each time and what each resistance is, and then the measured current. So our voltage is a constant 5 volts, but now with a 2 ohm resistor and a 1 ohm resistor, sorry, 2K ohm resistor and a 1K ohm resistor, we're measuring 1.68 milliamps. Okay. Now, let's see, what do we want to do next? Let's take out this 1K ohm resistor. Let me see if I can find another 2K ohm resistor. Oh, I've got one here. It's another red, black, red. Okay. So this is our circuit number 3. Two 2K ohm resistors. And what do we get? We're getting 1.27 milliamps. Okay. 1.27 milliamps there. All right. What else? What else can we do? So if we let me try and find a brown, black, brown. All right. So this is a 100 ohm resistor. I can get it out of my box. Here we go. So this is a brown, black, brown. If you can actually see it, this is a 100 ohm resistor. So now we have a 100 ohm resistor and a 2K ohm resistor. Yeah. And let's see what we are measuring off of what. So far, nothing. That is likely just because we're not making good contact. Oh, and because my circuit's broken. You gotta make sure to plug this resistor into the right row. There we go. All right, what are we getting here? It's like 2.24 milliamps. Okay. 2.24 milliamps there. Last one, so that's with a 100 ohm resistor and a 2K ohm resistor. Last one we're going to do is I'm going to take this 2K ohm resistor out and replace it with a 1K ohm. So now we've got a 100 ohm resistor and a 1K. Plug it in. Okay. And now when we measure this current, that we're going to get 2.28 milliamps. Now that is not what we expect. That appears to be limited because of the max output here. So I'm actually going to have to change up the circuit. So we are going to need to use a higher resistance. So let's see what we can do. Okay, so what we're actually going to do is we're going to put in a red, black, orange, this guy, if he ever shows up, if the camera can focus, there we go, which is a 20K ohm resistor. Okay, so now we've got that in this series with our 2K, so there's a 20K and a 2K. And what do we measure? Oh, sorry, I was putting that in the wrong place. Here we go. So that is giving us 0.24 milliamps. Okay. Great. So take those 5 measurements that we just took, and for each of them, we want you to use Ohm's law to calculate the equivalent resistance there, as if it was only one resistor in the system, right? So you're going to take V equals I times R. Our V was 5 volts in each of those cases, and our current was those values that we measured, and you're going to use that to calculate the resistance. Okay. Now make sure you're including the relationship between the equivalent resistance and resistance in series. Explain why this makes sense. Think about KVL voltages for series circuits from earlier, and how your pairs of resistances compare to the data you took earlier, and anything else interesting you find here, right? So once you've done that, we are going to move on to this parallel section. Okay, moving on here, we are putting 2K ohm resistors in parallel, and we're going to want to measure this voltage at 5 volts. Or we're going to want to measure this current at when our voltage is at 5 volts. Now, I'm actually going to change this a bit. I want this voltage to be down to 1 volt, just because I'm limited by my equipment here and the current that it can put out. And I know that if I keep this at 5 volts, it's going to very quickly skew our data. So I'm going to bring our current down to our voltage down to 1 volt, but we should still see the same relationship when we do this. Okay. So now we are going to build our circuit. Let me stop this so that we don't just have loose voltage. And now we need our 2K ohm resistors, which are the red, black, brown. Sorry, are the red, black, red resistors. That's these guys. Okay. And we're going to make them in parallel with each other. So that means they're going to share a row. We're going to share both rows, rather. Like so. Yeah. We're going to throw our ground on the bottom row, just like that. And our high current, our high voltage, I'll put here. So that way we can have our ammeter in between our voltage source and our 2 parallel circuits, just as shown in our PDF. So we've got 1 volt, and we are going to measure our resistance, or our current there, sorry. All right. It looks like we are measuring 1 milliamp, 1.01 milliamps. And we've got 2K resistors in parallel here. Right? So take that data and use Ohm's law to calculate the equivalent resistance here. And see if that makes sense to you, right? All right. So we know 1 volt is our source, 1 milliamp is our current. Use that to calculate the equivalent resistance. Right? Next, we're going to do the same thing. We want 5 data points, including that one we just took, where we are going to vary our resistances. So we're going to take out one of these and replace it with a 1K ohm resistor. That's our brown, black, red. Circuit number 2 here. And here we are going to measure 1.5 milliamps. 1.51 milliamps. All right. Now let me take out my other 2K ohm resistor and replace it with another 1K ohm. So now we have 2 1K ohm resistors in parallel. Measure that. Oh, sorry, I accidentally had this wired wrong. They weren't actually in parallel there. So we're measuring one resistor. So you got to be careful. Always check your circuits and make sure they're built correctly. It's easy to make small mistakes. So now we've got 2 milliamps going across this. Okay, so that's our circuit number 3. All right. Okay, so for current number 4, we're going to switch things up a little bit. We're going to take one of these really big resistors, brown, black, yellow. This is a 100K ohm resistor. It's very large, obviously. And we're going to put that in parallel with a 2K ohm resistor. We're going to see what we measure out for that. 2K ohm, of course, being our red, black, red. Okay. So now when we measure this one, what current are we going to read? It looks like 0.51, 0.52 milliamps there. All right, so make sure you record that. We've got a 100K ohm resistor here and a 2K ohm resistor here, and we're reaching about 0.5 milliamps. Okay. And now we're going to just take the same circuit, but with a 1K ohm resistor in parallel with that 10K ohm or 100K ohm resistor. And what do we have here? 1.02 milliamps. Okay. All right, so that is our 100K ohm resistor in parallel with a 1K ohm resistor. So for each of those data points that we just collected, we want you to use Ohm's law to predict what the equivalent resistance is. So you're going to predict what that resistance would be if it was only one single resistor there. Same thing as with our last circuit, right? And now you're going to want to use this equation, which is going to give you the equivalent resistance of 2 resistors in parallel with each other. Right? You should have learned this equation here in class before. All right, and then you want to answer these last few questions here based off of what we just did and work through your conclusion. All right, so then all you have to do after this is come to a lab session, one of your Zoom lab sessions, and meet with your TA. They're just going to check through your work and make sure everything looks good. They'll probably ask you some questions to make sure you understood everything. And that is that. Remember that these checkoffs are worth 50% of your grade for these lab assignments. So please make sure that you're doing them. They are just there to make sure that you get the most points possible and to make sure that you understand everything in the lab, right? And so, yeah, and after the checkoff, we allow you to do a resubmission. So if you aren't happy with the grade that you get during your checkoff, you are welcome to resubmit for even more credit. All right, great. I look forward to meeting all of you in our Zoom sessions later, and I hope this video is helpful.